I hope you are all well and healthy and ready to learn a new things. So my name is Palak Patel. I am working in the Mahatma Gandhi Institute of Technical Education and Research Center, Navsari, in Civil Engineering Department. I am going to teach you the subject is design of structure. This subject this subject is subject code is 3150612 and this subject included in BE third sem fifth. So in this lecture we are going to learn a singly RC beam design. So shall we start? Here are the design step of singly RC beam. For the design of singly RC beam, first of all we have to select size of beam. Then after select material of the structure. Then after find a load on a beam and convert it into a factor load. So first of all, these are size of beam is assumed. It's assumed by us, okay? And material it's also assumed. Both of things are assumed because we don't know which size of beam we needed. We just assume this is 300 by 350 beam or 230 by 300 beam. These are assumed, okay? There are no criteria about in size and depth. So these are the assume, okay? And material also assume. Okay. Now after select size and material, we have to find a load on beam. Which type of load? Live load, dead load, wind load. Okay. And this load converted into factor load. I discuss about why we convert it into factor load. Because we assume 50% more load than actual applied on a beam. We design a structure for the 50% more than actual applied load on the beam. Okay, so this 50% more load called as factor load. Okay, then after find a factor load, we have to calculate maximum bending moment, which is called is mu. Why we need a maximum bending moment? Because we design a structure for the maximum bending moment and the limited moment will be safe if you design a structure for the 10 kilonewton into meter moment. You design a structure for the 10 kilonewton into meter, okay? And if your structure can resist 5 kilonewton into meter, so that's why we calculate maximum bending moment on beam, okay? And after find the maximum bending moment, we have to design a structure for the balance section. For the balance section, and balance section condition is here: mu is equal to mu limit. Mu is equal to mu limit. We have the mu limit equation, limiting moment equation, okay? And after a moment limit equation, we have to find a missing data. Missing data means a depth or width or anything else. We have to find it. First of all, we assume it a size of beam. Here is a width or depth we assume, but these are the check. These are the check. If I am assume a 350 depth of the beam and check by mu is equal to mu limit, then my depth value is 400. That means I have to revise all the data from here. Means I assume a depth of beam is 350 okay? But while we are checked by this, mu is equal to mu limit, I found a depth which is 400 mm. Means this depth is not to be included, is not safe. So by that depth of 400 mm, we have to revise the whole structure by the 400 mm depth. Okay. After mu is equal to mu limit, we have to find pt. These are the equation of pt. pt into fck upon y into 1 minus under root 1 minus 4.6 mu upon fck bd square. Upon fck bd square. By find pt, this equation is percentage of steel. After find pt, we provide this value in this equation. This equation pt by 100 into b into d, it's give area of steel. It's give area of steel. After a find of area of steel in a tension zone, we have assumed a bar diameter, means a 10 mm bar or 12 mm bar. We assume this data. Okay, assume bar diameter. And small ast we found. Small ast means a cross section area of bar, means this bar is round shape, so we found this area, cross section area of bar. If I assume 10 mm diameter, 10 mm diameter bar. Okay, so small st is what? Pi by 4 into 10 whole square. These are the small st. If I assume 12 mm diameter, pi by 4 into 12 whole square. Okay, these are the small st. And find the numbers of bar, we have to divide capital st divided by small st. Capital st means area of steel which is required, and small st is diameter of bar, area of bar. Okay, and by this equation we got numbers of bar. Okay, so this is the first example for the design. So design a reinforced for the rectangular RCC beam 200 mm wide, simply supported beam over effective span 3.5 meter, loaded with service load of 40 kN, including self-weight. Draw sketch of cross section of beam. Okay, so first of all, design. These are the given data. fck is 20 Newton per mm square, fy 415 Newton per mm square. These are the material which is assumed by us. This value is not given in the example. So we assume my material, my concrete grade is M20 and steel grade is Fe415. These are assumed. Okay, then after factor load. So what is factor load? W into 1.5 into 440 is the service load, including self weight. 40 into 1.5, so 60 kN per meter is factor UDL, factor load. So by the factor load we can find a moment. 60 into 3.5 whole square is the length, and divide by 8. So these are the moment, 91.875 kN per meter. These are the maximum bending moment. Why we use the WL square by 8? Look at here, students. We assume beam support is fixed. And your load is UDL. So we have a two conditions. One is a fixed support, and second with UDL. So what is the maximum bending moment for a fixed support and UDL? It is maximum bending moment is WL square by 8, which is in the center. Okay, that's why we found the moment by WL square by 8. Okay, then after design the balance section. So Fy is 415. So first condition is for the balance section, mu is equal to mu limit. So mu limit, so this is mu and here is mu limit, both are same. For the 415.138 FCK BD square, This equation we will find it in the singly reinforced beam analysis section in the previous lectures. Okay, we provide all the values here. Mu limit 0.133, 20 fck, width 200, depth we will find a depth, missing depth, so d square, so depth is equal to 407.97 mm, so we assume depth is 410 mm. Then after find AST, for find a capital AST we have to find mu upon bd square. Mu upon bd square, these are the important equation. For the all time we have to follow this equation. Mu upon bd square 91.875 into 10 raised to 6 divided by 200 into 410 whole square. B and D which we found it, look at here, 410 B and D both are here. So by the mu we got a value 2.73. For the 2.73 we have a PT value, found a PT value. PT is equal to percentage of steel. So these are the equation. 50 into FCK upon Fy into 1 minus under root 1 minus 4.6 mu upon FCK BD square. Provide the value here. Mu upon BD square is from here 2.73, FCK 20, Fy 415. So PT is 0.93.9 percentage. So what is this 0.93.9 percentage? We call it as the percentage of steel. We called it as a percentage of steel. But what percentage? Cross section area of beam. Cross section area of beam. Look at here. Your beam is look like this. These are the cross section area. Okay, these are the 100% here. Okay, it's 100% cross section of beam. So what is your 0.93 means this little bit area. Is it called 0.939 percentage? Okay, so this type we assume as a cross section of beam. Percentage of steel is depend on the cross section of beam. Okay. Then after AST, area of steel, by the percentage of steel we have to find area of steel, PT by 100 into B into D. So provide a PT value, percentage of steel, we will find the area of steel 769.98 mm square. These are the total area of steel in a tension zone. Look at here, AST, area of steel, and T for tension. Okay, so when we found AST we have to find, we can call it area of steel in a tension zone. Okay, and then after we assume a 60 mm diameter bar. So what is the small AST? 201.06 mm whole square. 201.06 mm whole square. Then after number of bar, capital AST upon small AST, 769.98 divided by 201. So 3.82 numbers of bars. How we provide 3.82 numbers of bars in a cross section area? So we provide 4 numbers of bar. Always take a more value than this value. Okay. Not we take a 3.82, so provide a 3 numbers of bar. It's not correct. If your value is more than a 3 point something, then we have to apply 4 numbers of bar, more than a 3. If you take a 5 numbers of bars, then will be okay, your design is safe. But you can't take 2 numbers of bar or 3 numbers of bars. Okay, depend on this value. Okay, understood? Simple. Then after find the area of steel provided, we require 3.82 numbers, but we provide 4 numbers. So what is the 4 numbers area of bar? How many area is covered by steel in a cross section? So this area is 804.24 mm whole square, which is more than required. So your structure will be safe. After we have to draw some cross section. Okay, yeah, we have to draw some cross section. Students, maybe my drawing is too bad, yeah, it's too bad. I need to improve it. Two, three, four. Okay, four numbers of bar we provided. So what we have to do, data is here. Okay, look at here. We width 200, effective depth 410, cover 50 mm. Draw this diagram, is compulsory in the exam point of view. Write down 4 main reinforcement here. Main reinforcement, 4 numbers of bar with 60 mm diameter. Okay, then these are anchor bar. Anchor bar is 2 numbers of bar with 10 mm diameter. These are the cross section of beam which we design at this stage. Okay, these are the cross section of beam. Okay, the second example here, design a singly reinforced rectangular beam, factor moment 160 kilonewton per meter. Here provided direct moment provided, so we don't need to calculate mu here. This mu is given. And look at here, use Fe415 steel, concrete, effective width and depth ratio of beam is 0.7. 0.7. So given data is here, FCK20 F5415, its concrete grade is steel grade, factor moment is given 160 kilonewton per meter. Direct moment, we don't have to calculate by a load or something else. This moment is given, so we don't need the equation WL square by 8 for find mu, because mu is given, factor moment is given in the example. So look at here, one more thing is given, effective width depth ratio, width by depth is equal to 0.7, so B is equal to 0.70, B is equal to 0.70. These are the given in the example. So for the balance section, we have the mu limit. So direct mu limit is equal to 0.138 FCK BD square. Provide a value, mu limit is 160, 0.138 FCK 20. D is 0.70 or D square. So D cube. We found D here 435.88 mm. So we assume a 440 mm. Effective depth 440 mm. So we have the condition here, B is equal to 0.70. By this equation we can find a width 308 mm. Consider effective cover 40 mm. So D plus 40, 480 mm. So we have a cross section of beam here. Look at here guys, we have a cross section of beam. Here is 308 mm, width, cover 40 mm, effective depth 440 mm, and overall depth, capital D is overall depth 480 mm. So these are the cross section of beam is completed. Cross section of beam is completed. Okay, by the cross section of beam we have to find the area of steel. So first of all we need a mu is equal to, now mu upon BD square, 160 into 10 raised to 6 divided by 308 into 40 whole square, 2.68. These are the MU upon BD square equation. Now we are going to SP60 page number 48 table 2 for find PT. SP60, I have XP60, look at here, SP60, which page number? Page number 48. It's 27, 30, 48, page number 48. Where is, yeah, page number 47. Look at here, students, I will explain how to read the SP60 for the finding PT. Okay, first of all we have to remember the value of FCK. We have 20 Newton per mm square FCK. Concrete grade is M20, so FCK 50 here. So this table will follow the FCK 50, but we have a FCK 20. So look at here, FCK 20 here, FCK 20. So this table we can use, but we have a FY 415 is also included. 415 is also included. 415 is also included. Okay, so we can follow this table. We can follow this table, both table here. Okay, so remember MU upon BD square value. What is MU upon BD square value? 2.68. So look at here, these are MU upon BD square 2.60. These all values are included. MU upon BD square, which value we have? 2.68. look at here, 2.68, 2.68 here. here. Then FE415 means this value, and 2.68 means these values. So this row, this column is matches is here. This row, this column matches here. So 0.919, 0.919. So these are the PT. 0.919 is PT. So provide a PT value in the equation. AST is equal to PT by 100 into D into D. We got a value of AST 1245.42 mm whole square. 1245.42 mm whole square. These are the area of steel. So we assume by area of steel we assume 20 mm diameter bar. So what is the here? Small ast 314.50 mm whole square. Pi by 4 into 20. Why bar is in a circle? Bar is in a circle. So what is the area of circle? Pi by 4 into diameter. Pi by 4 into diameter whole square. So these are the equations. So by the find capital ST, small ast, we got a value 3.96, approximately 4 numbers of bar. So provided area of steel 4 into cross section area of bar 4 into 314.50. So over provided area is 1256.6 mm whole square. Required is 1245.42, but we provide 1256.6 whole square mm square. So beam is safe. Now we have to draw some cross section. Look at here. Width is 308. Effective depth is 440. Cover is 40 mm. Cover is 40 mm. So overall depth is 480 mm. So here as main reinforcement. Main reinforcement. Main reinforcement is 4 numbers of bar is 20 mm diameter. 4 numbers of bar is 20 mm diameter. So here as anchor reinforcement. Anchor bar is provided for the stirrup support only. It will not resist any type of load. So anchor bar is provided for the stirrup. So we provide only 2 numbers of bar as 10 mm diameter. 2 numbers of bar at 10 mm diameter. Complete. These are the cross section area of beam. Cross section area of beam. Completed. 2 example is completed. Now there is a third one. Third one we have to read it out. Design a rectangular RC beam. 1 second, I will change the color. Okay. Rectangular RC beam having width 250 mm. Width is given. Simply supported beam, effective span 4.5 meter. Loaded with UDL 20 kN per meter, including self weight M20 grade concrete ने Fe 250 grade steel. M20 grade concrete ने Fe 250 grade steel. Check the beam for maximum and minimum steel and deflection. So we have to follow the check in this example. Okay. So these are the given data. M20 grade steel. M25 grade concrete. Fe 250 grade steel. So factor UDL is 1.5 into 20. 20 is UDL load is given. So by the factor load we got 30 kN per meter. It's factor load, UDL factor load. Then after MU limit 148 FCK BD square. This value we discussed in the previous lecture. So by provide MU limit 1.48, 25, 250 D square. D is equal to 286.50 mm. 286.50 mm. So by this equation we got a depth is 300 mm. So we got a cross section here. Effective cross section here. Width 250. Depth 300. Width 250, depth 300. Okay. Then after provided 50 mm cover. Providing 50 mm cover. So what is the overall depth? Is 350. So here we provide cover is 50 mm. So overall depth is 350. Simple. So this is the cross section of beam is completed. And after we have to find area of steel by this equation. Mu upon BD square. Mu is 75.93 into 10 raised to 6. Divide by 250 into 300 whole square is equal to 3.37 is equal to 3.37. Once again we have to follow the IS code SP60 page number 48 table 2. Same value is here. FCK 20 included. FCK 20 included. F security here, but Fy is 250. We have a 250. We have a 250 Fy. So let's check what is the mu upon bd square. 3.37. Mu upon bd square is 3.37. What is one? Okay, sorry. FCK 25 here. Okay, my mistake. I'm sorry. We have a FCK 25, not a 20. FCK 25. Okay, sorry, my mistake. So FCK 25, we got a value 3.37. We have a 3.36, 3.38, and what is the value of Fy is 250. We have to follow this column, second column. Okay, 3.36, 3.38. So we have a two value here, 1.194, 1.192. Whichever you want to take as little, you can take it, or take it as average value 1.914 or 1.929. Take it as the average value, or you can take it both value. So I take it here, PT is 1.922 percentage. These are the average value of both value. So provide PT value here, AST PT by 100 into P into D. So PT is 1.922 into 250 into 300 divided by 100. So by the AST, we got AST 144.15 mm square. 144.15 mm square. These are the area of steel in a tension zone. So provide a 20 mm diameter bar. So what is AST? 314.50 mm square. So numbers of bar is 5 numbers, and 5 into 314.50, 1570.75 mm square. So these are the completed cross section of beam. Beam design is completed. Now we have to follow the check. Minimum and maximum steel and deflection. So minimum steel in the beam, we have a IS 456 2000 to page number 47. Page number 47. Here is IS 456 2000, page number 47. 36, 39, 30. Page number 47, look at here. This is the equation for to find the minimum steel. AS into upon P into D is equal to 0.85 upon Fy. So by provide all value, we found the AST minimum is 1255 mm square is minimum. We cannot provide 255 mm square cross area steel minimum less than this value. Okay, 255 mm square. These are the minimum of area. So we provide more than the 255. And the maximum steel in the beam. So maximum steel is a 4% of cross section area. 4% of cross section area. These are the criteria of maximum steel. 4% of cross section area. So 0.04 into B into D. 0.04 into B into D. So we got value 3000. Okay, if you miss this value, this equation, if you miss this equation, just remember 4% of cross section area. How to calculate this? PT by 100 into B into D. Provided PT is 4 by 100 into B into D. 4 by 100 0.04 MBD. You can get this equation. Simple. If you can't remember the equation, just clear it is some concept. Maximum steel is 4% of cross section area. Okay, so 4% provided 300 mm square. These are the maximum 3000 mm square. These are the maximum cross section of the steel in a tension zone, and we provide 15 something 156.6. Okay, these are we provided. So by the minimum we can assume we can't provided the value, we can't provided a steel less than 255 mm square. We cannot provide it. Okay, and we cannot provide it more than 3000 mm square. Remember, if you design a structure, you cannot provide a beam less than minimum or more than maximum. Maximum is 4%. Okay, minimum by the equation which we learned earlier. So remember this both the thing. So your structure is safe. Okay, then after check for deflection, actual length by D, actual length with actual length of beam and actual depth of beam, length divided by depth. So we got value 4500 length, 4.5 meter length. So in the mm 4500 divided by 300, we got actual L by D is 50. Okay, then after find PT we found earlier, but this time we assign a steel more than required. We required 4 point something, 4.9 or something, but we provide 5 numbers. So by the 5 number, percentage of steel will be changed. So we found actual what we provide percentage of steel, actual provide in the beam. So 100 into 1570.75 divided by 250 into 300. So we got a value PT is 2.90 percentage, 2.90 percentage, and maximum length by the F ratio is 2195. How we got this value? By the chart SP60 page number 44, 8. These are the 45. Okay, here is 44. Look at here, these are the graph here. Okay, we found a maximum ratio of span and effective depth. We will found this. Okay, we have to found this value. So by this graph, FCK is 25. FCK is 25. What is PT? Percentage of steel is 2.09. 2.09. Look at here is PT 0.5, 1, 1.5, 2.0. Here is 2.1, 2.2. So where is 2.09? Where is 2.09? Between these two. Between these two, 2.09. So I follow this line and meet it here. So by this graph, I can found value is more than 20. More than 20. Okay, this graph give a value more than 20. So I just approximate value is 21.95. It's approximate value. You can take it 20 or something else. Is important is more than 50. It's important. Your value is more than 50. Actual length by depth is more than is lesser than maximum length by depth. So a structure is safe. If I take his length by d not is 21.95, I will take his 20. So what a difference? Is more than 50. Actual length by depth is lesser than maximum length by depth. These are the conditions. Actual length by depth is lesser than maximum length by depth for the safe for your structure. Understood? So actual length by depth, maximum length by depth, both are safe. So your structure is safe. Okay. We have to draw some cross section of the beam. Here is a cross section of the beam. We have 1, 2, 3, 4, 5. 2 anchor bar, 250 width. I think effective depth is 300. Yeah. A second, may I check it out? Yeah. And main reinforcement is 5 numbers of bar at 20 mm diameter, and these are the anchor bar, 2 numbers of bar as 10 mm diameter. Completed. So these are the cross section of beam which is completed. So our design of singly beam chapter is completed. In the next lecture we learning a doubly beam design. What is WRC beam? I will explain it in the detail. So wait for it. We will meet soon.